Hi, grade 11 physics class. Welcome to another video lesson on kinematics, and today we're going to talk about motion with uniform acceleration. Okay, so kinematic problems which involve accelerated motion, they can become complicated, but they're less complicated when you properly apply some key equations. And to help us derive some of these equations, we're going to look at graphs through this lesson, since we have a pretty good understanding of motion as their motion is represented by graphs so far. So let's get started. So first of all, calculating displacement. We know that we can calculate the displacement of an object's motion by finding from the velocity time graph the area under the curve, right? So in a case like this, so this red line represents an object which is with constant acceleration. We know it's constant acceleration because it's a straight line with a slope. And so velocity is changing as time goes on, and so therefore that's accelerated motion. So the area under this curve is going to give us the displacement of that accelerated motion. So to calculate the area, we can try to do it all in one chunk, but another way we can do it is to divide it up into two areas. So it's kind of like we've got area 1 here, we've got area 2 here. Area 1 we'll just calculate by saying area is base times height. In this case, the base is the change in time. Okay, so we go from initial time to final time. And so that's going to be our delta t. So the delta t times the height here. And that's going to be initial velocity minus basically 0. Okay, so the height is just going to be the initial velocity. And that's the area of area 1. Area 2 is going to be this triangular area over here. And so we calculate that. Area of a triangle is half base times height. So we're going to multiply half delta t, which is this length here, times the height of this triangle, which is the final velocity, subtract the initial velocity from this red line. Okay, so the total area that's going to give us the total displacement, so it's going to be initial velocity times delta t to get area 1 plus half delta v, v final minus v initial, that's the height of the triangle, times delta t, that's the base of the triangle. Okay, so putting those things together, rearranging the equation a little bit, multiplying through by the half and the delta t, we get 1/2 vf delta t, subtract 1/2 vi delta t. Okay, and rearranging a little further, so collecting some like terms, we've got vi delta t here, negative 1/2 vi delta t here, so in total, half vi delta t plus half vf delta t. And rearranging that equation, we arrive at displacement is equal to vi plus vf over 2 times delta t. Basically, we factored out the half and we factored out the delta t from both terms here and combined it to create this equation here. Now I've started here and said that for this equation to be valid, the acceleration must be constant. That's because we're calculating the area under this triangle and assuming that this is a straight line. If acceleration wasn't constant, then this line would not be straight. It would be a curve as opposed to a line. Okay, so we'd have to use something else to calculate area under the curve. But for accelerated motion that's constant, we can use this equation. So displacement, vi plus vf over 2 times delta t. Here's our first example to use with equation 1. So a car accelerates from 10 meters per second east to 15 meters per second east in 30 seconds. How far did the car travel during this time? So we're going to employ equation 1, delta d vi vf over 2 times t. And plug in the values. The initial velocity is 10 meters per second. Final velocity is 15 meters per second. Basically, if we take 10 plus 15 over 2, it's kind of like we're taking the average velocity and then multiplying the time that the car was accelerating over. if you think about it in terms of the graph, that makes sense. We're basically taking the average of these two values, so the spot right in the middle of the curve, and multiplying it by delta t across the graph. So it's kind of like we're taking the area of a rectangle, if we think of it that way. Okay. So that works out to be 25 over 2 times 30, 375 meters east. So our change in our displacement, our change in position is 375 meters east. Next, we know the definition of acceleration is the change in velocity over time. So it's the rate of change in velocity. So it can be rewritten as final velocity minus initial velocity divided by time. Okay, or rearranging, we can say that Vf minus Vi is equal to A times delta t. Just multiply both sides of the equation by delta t. And so solving for Vf is equal to Vi was taken over to the left side and made positive, Vi plus A delta t, and then just rearranging this equation, Vf is equal to Vi, final velocity is equal to initial velocity plus acceleration times the change in time. And that's our equation 2. And again, equation 2 will only work as long as acceleration is constant. Okay, and if you think about this equation in terms of this velocity time graph, it makes a lot of sense. What we're saying is the final velocity is going to be equal to the initial velocity, so this velocity plus this velocity. This can be represented by acceleration times the change in time. Acceleration is in meters per second squared. Meters per second squared times time, which would be in seconds, gives us meters per second. That's velocity. Okay. So that was our equation 2. So here's our first example to go with equation 2. Example B, a car moving at 10 meters per second east accelerates at 2 meters per second squared for 8 seconds. So what is the car's final velocity? Okay, well there's our equation. Substituting some values into that equation, it's got an initial velocity of 10 meters per second, but it accelerates at 2 meters per second squared as 8 seconds goes by. So 2 times 8 will give us 16. So if we add 10 and 16 meters per second, our final answer for this question will be 26 meters per second east. Okay, now we're going to take equation 1 and we're going to take equation 2 and we're going to mash them together. So we're going to take the Vi plus A delta t and substitute it in for the final velocity here in equation 1. Here we go. What that will look like now is displacement is equal to initial velocity plus A delta t over 2 times delta t. Okay, taking that a step further, simplifying it a little bit, we added the two Vi's together. So we've got 2 Vi plus A delta t all over 2. Multiply that by delta t. So our final line, what we arrive at here, the two 2's cancel for the Vi. So we're left with Vi delta t. And the second term, we're left with 1/2 A delta t squared. These two delta t's were multiplied together. So A delta t squared at the last term here. That's going to be our equation number 3. And if you think about equation 3 in terms of the velocity time graph, what it's basically saying is term 1 here is Vi delta t. That's the area of the rectangle here, Vi delta t. The base of the rectangle is the delta t. The Vi is the height. And the second part of the equation here is the 1/2 AT squared. So the base is a delta t. The height is A delta t. So to calculate the area of the triangle, it's 1/2 times the base times the height, a delta t, which equals 1/2 a delta t squared. So equation 3 makes quite a lot of sense.